In this video, we will give a review of hyperbolas, and I want to focus initially on describing where does the equation of a hyperbola come from. Okay, so the setup is I'm going to let P and Q be points in the xy plane. So I'm going to draw a picture of some axes. So I'll draw a y-axis and an x-axis. And so this is the same sort of setup initially as we did with ellipses. These 2 points are called foci. So I'm going to draw 2 points, P and Q, and just for simplicity's sake, I'm going to put them both on the x-axis and equally spaced from the origin. So they don't have to be like this. If I wanted them to be arranged sort of vertically or slanted diagonally, we could, but I just want to draw it like this for simplicity's sake. All right, so now I want to consider all points, x comma y, such that the distance from the point xy to the focus P, and remember that foci is just the plural of the word focus. We mentioned that in the last video as well on ellipses. I'm just reminding ourselves of that. So that's what foci is. So a parabola has one focus. An ellipse and a hyperbola have 2 of them. So we say they have 2 foci. Okay, so we are considering all points x comma y such that the distance from x comma y to P, this time I'm going to subtract the distance from x comma y to the other focus, to Q, and I want that distance to be a fixed constant, d. And in this setup, I'm going to require that d is a positive number and that it's less than the distance from P to Q. So it's less than the distance of that line segment, PQ. All right, so if we draw some points with this property, so I'm going to begin by drawing sort of like an arbitrary point with that property. So if I draw a point here, let's say, and let me call this x comma y, and I connect it with P, so the distance to P, the focus P, and I connect it with the focus Q, I need the distance from it to P, so I'll call this thing D1, and the distance from it to Q, I'll call that distance D2. I need D1 minus D2 to always be equal to this fixed number D, whatever D happens to be. Okay, so what do other points look like that keep that difference in these 2 distances the same? So let's just say hypothetically this was a number like 3, that was that distance, and D2 was a distance like 1. So if I were to decrease D1, so in this case their difference is 3 minus 1, which is 2. So I need to keep that difference 2 no matter what. So if I were to decrease the 3, I need to decrease the 1 as well. So that would be somewhere maybe here. You know, when I draw that point, it has a smaller distance to P, but it also has a smaller distance to Q. And if I keep going like that, I could decrease it a little bit more if I put something here that has a smaller distance to P and a smaller distance to Q. On the flip side, if we wanted to increase one of them, if I wanted to increase D1, I'd have to increase D2 as well. I would need to put a point like that somewhere maybe here. That increases the distance to P and to Q. And if I start to connect these points, my graph will start to look like this. And I'll also have something similar to that going on over here. All right, that's not the only place where I can draw something like this. If I were to draw, and I just realized there's something I'm missing in this equation right here. So what I'm missing is I need an absolute value around this. So it turns out that the difference in these 2 distances in absolute value needs to be equal to D. And when I have the absolute value in there, that means if I take points on this side, so like a point here, the mirror image, another point like this, another point like this, they also satisfy this equation now. They also satisfy that equation. Okay, and that will give me a shape like this. basically when I have points on this left-hand side of the graph, it switches the roles of the d1 and the d2. So whereas on the right-hand side, d1 minus d2 was a positive number, like 2. On the left-hand side, there will be a negative number, like a negative 2. Okay, so that gives me this graph of this hyperbola. Okay, so this graph is a hyperbola. All right, so I'm just going to clear up some of these extra markings that I've made in the graph so it reads cleaner. All right, so I've just cleared off some of those extra markings there. Okay, so what's the equation of a hyperbola? So the equation of a hyperbola with a focal axis. So by focal axis means the line that connects the two foci, so in this case the line connecting P and Q, being parallel to the x or the y axis is, so it could have one of two forms. It could look like x minus x naught squared over a squared minus, that's the key difference between this and an ellipse, the minus sign. So similarly for, whoops, sorry, not over 2, it would be over b squared equals 1. So it could look like that, where I have the x terms and then minus the y terms. Or it could be reversed, and I could have the y terms in front. So y minus y naught squared over, all right, b squared minus x naught squared over a squared being equal to 1, where the point x naught comma y naught is the center. So the center is the point halfway between the two foci. Okay, so halfway between the two foci, that would be right here. That is the center. And in this equation, the a and the b are positive numbers. So an ellipse, when its focal axis is parallel to the x-axis or parallel to the y-axis, it can have one of these two forms. So it looks, sorry, did I say ellipse? I meant to say hyperbola. A hyperbola could have one of these two forms. So I either need a negative in front of the y squared terms or a negative in front of the square terms in front of the x. So let's do an example. Let's graph 9x squared minus y squared equals 9. So there's some optional stuff that we could do at the beginning just to convince ourselves this is an ellipse, which is we could divide by 9 to get this in standard form for a hyperbola. And if we did that, if we divided both sides by 9, we'd get x squared minus y squared over 9 equals 1. And now this looks like the equation of hyperbola. Okay, so the next key step is to help us graph this, we find the intercepts, just like we did with ellipses. So I could have gone into this finding intercept step right from the beginning. That's why I call these first two lines optional. I just did the first two lines to really convince myself that this was a hyperbola. So if we find the intercepts, let's get the x-intercepts first. So let's set y equal to 0. And when we do that, we get 9x squared equals 9. And isolating, we get x equals plus or minus 1. So the x-intercepts are 1, 0 and negative 1, 0. Now let's find the y-intercepts. So for the y-intercepts, we set x equal to 0. And setting x equal to 0, we end up getting negative y squared equals 9. So for both of these, I decided to use the original equation just because it didn't have fractions, so that looks simpler to me. And then if I move the negative over, we get y squared equals negative 9. But that has no solution. No solution since y squared is always greater than or equal to 0. It's never going to be negative 9. I could also arrive at that answer and see that if I were to square root both sides, I get the square root of a negative number, which is impossible. So, because we're not allowing complex numbers for what we're doing here. So that would also have no solution if I decided to square root both sides. I could have seen it that way as well. So because that has no solution right there, in terms of the y-intercepts, that means there are no y-intercepts. All right, so let's use these facts to help us graph this. Okay, so let's draw some axes. So draw some axes, an x-axis and a y-axis. So there are two x-intercepts. There's one at 1, 0, another one at -1, 0. The fact that there's no y-intercepts means the ellipse has this type of sort of horizontal shape. Sorry, I keep switching up ellipse and hyperbola. It means a hyperbola has this sort of horizontal shape. And that is my graph right there. If we had tried to find these intercepts, and there were y-intercepts, but no x-intercepts, what that would have looked like is, if I draw some axes, it would have looked like a hyperbola like this. This one has y-intercepts, but no x-intercepts. It would have looked sort of vertical like this. We could also have slanted hyperbolas as well, and let's do an example of some of those, because there are some really common slanted hyperbolas. So here's the example I want to do. Let's graph the following on the same set of axes. So we have these 4 equations, and I want to draw their graphs on the same set of axes. So the first thing I'll do is I'll just isolate y in each of these. So in the first one, I get y equals 1 over x. And that equation looks familiar. We know what the graph of this is. With the next one, if we divide x, we get y equals 2 over x. For c, we get y equals -1 over x. And for d, we get y equals -2 over x. All right, so now let's draw some axes. Let us draw some axes. And let's draw these hyperbolas. And for this, pause the video for 2 minutes and try this on your own for review before we do it together. 4, 3, 2, 1, pause the video. Pause the video for 2 minutes and try these on your own. Try to graph them on your own before we do it together. All right, so hopefully you've done that. Hopefully you've paused the video for about 2 minutes to try these on your own first. All right, so let's graph these. So let's start with a graph of 1 over x. So 1 over x, we know that that graph looks something like this. And one of the points that it goes through is 1, 1 here. And it also has a portion of the graph over here. And on this side, it goes through the point -1, -1. So this is a hyperbola. It's just slanted. Okay, so with the next graph, when we have 2 over x, what that is it's actually 2 times 1 over x. And what that's going to do, what this 2 is going to do is, it's going to stretch. It stretches the graph vertically. And it's vertically because this is what y equals. So putting the 2 in front of the 1 over x is going to double what y equals. That's why it stretches it vertically by a factor of 2. By a factor of 2. So I'm going to double all the y coordinates of the points. So for this point, 1, 1, now that's going to be at 1, 2. And when we draw the rest of it, it'll look, let me draw a little bit more. So going up and then going this way. Okay, so I get something like that. And then on the bottom of it, when I take this y value and I double it, I get 1, -2. And then drawing my hyperbola, it looks something like this. It looks something like that. So it has the same asymptotes. It's just stretched out vertically more. Okay. When we put a negative in front, like -1 over x has, this is a reflection of the first graph. It's a reflection of this first graph across the x-axis. So we're going to reflect this first graph that we drew in black across the x-axis. So when we do that, this point here that was at 1, 1 will now be lower. And that part of the graph will look like this. It'll get flipped across the x-axis. And that point is now 1, -1. If I do the same thing to this other black portion, that point will flip up. And then my whole hyperbola part there will flip up. And that point is now -1, +1. So finally, there's one more of these. The -2 over x will take the graph of -1 over x, and it'll stretch it vertically by a factor of 2. So this point, instead of being at 1, -1, will now be at, well, let's draw that a little bit better. That one will be at 1, comma, negative 2. And that'll look something like this. And then for the point that's at negative 1, comma 1, that point will now be at negative 1, comma 2. And my graph will look something like this. Something like this. That one's negative 1, comma 2. Okay, so that's not perfectly to scale, but still, that's the idea of what these graphs look like. Okay, so we've talked about circles, parabolas, ellipses, and hyperbolas in this section. So these are all examples of what are called conic sections, these shapes that we've looked at. In the next section, we are going to look at 3D versions of these shapes, of these conic sections, and they are called quadric surfaces. Quadric surfaces. So in terms of our goals for this section, we have now talked about hyperbolas, where they come from in terms of the geometry, in terms of distances, and done some examples to review how we graph them.